Okay. So in the first part, I've described the concept of sparsity and compressed sampling, and then I've started to describe the first kind of dictionary that have been proposed, which is the wavelet dictionary. And what you have seen is that it is the continuous wavelets. Continuous wavelets are very easy from the conceptual point of view. It's easy to compute, but every time you want a given scale, you have to recompute the convolution product of your data with your wavelet function, which is not very convenient. So what I'm going to present now is two or three different wavelet algorithms, which are, each of them is a kind of dictionary. So you will see that already even in the wavelet family, you can have different dictionary with different properties. And this is what I'm going to show you now. And tomorrow I will maybe present curvelets or other decomposition. So the whole idea is still to have a linear decomposition on the dictionary phi, as you have seen. So data are equal to phi alpha. And what you also want is to have a fast decomposition, like we have with Fourier, n log n to go from the data to the Fourier coefficients. Can you have the same with wavelets? And this is what I'm going to show you now. This is but to understand how we can have fast algorithm, you need to understand this what you call theory of multi-resolution. And the idea between this is to introduce space related to the resolution where we are. So we say that the data we have belongs to a given space, and when we when you decrease the resolution, then the new data belongs to another space which is included in the previous one. So you will start with data which are in V0, and when you degrade your data, when you decrease the resolution, your new data set belongs to another space, V1, V2, V3, as soon as you degrade your resolution. So you have to understand this space, and then now you have a space in the math definition, then you can define a basis for this space. And the basis will be this function phi, which is called scaling function. So you had the wavelet function before, now you have also the scaling function. And the scaling function will define a basis for the space where you are. And when you go to a coarser and coarser scale, then the basis function will be defined by this way. And you will see that these basis functions are related to a mother function, phi. And phi typically can be seen as a low-pass filter. When you go to coarser and coarser scale, the function phi just decrease the frequency band. Okay, so it's a low-pass filter, and you degrade your resolution. So now, to understand what it means, so you have your data, and then when you lose some information, some resolution, then the data became smoother and smoother. And if you look at discrete data, because you have less and less information, then you can remove 1 pixel out of 2 at each resolution step. Okay, so you have to really to understand this. You start with data, you smooth the data, and you divide by 2 the resolution. But because you divide by 2 the resolution, you can also remove 1 pixel out of 2 in the same time. So you can represent the same amount of information. So you have n pixels. You can represent the same amount of information with n over 2, n over 4, and so on. And then you have a multi-resolution approach on your data. So now, when you degrade your data, you lose some information. And the information you lose between 2 resolutions belongs to another space. And this space is called O. And when you degrade, so when you are in VJ, so when you degrade the resolution, you go to VJ plus 1, and the lost information is in the other one. And then, for this new space, you have also a basis, and this basis is defined this time from the wavelet function. Okay, so the wavelets represent a basis for the information lost between 2 resolutions. You have to understand this. And then you can get the wavelength coefficient just by convolution, a scalar product between your data and this scaling function. Yes? I will come back. In fact, it's even worse than that. You are not using the wavelets and not the scaling function. You will see. I will show you how you do that. But the point is, what is important is you understand what you have in hand at the end. So here, you have the space for when you degrade the data. Each signal belongs to a given space, and the lost information belongs to another space. And this other space is related to wavelets. Is the information lost between two resolutions. So coming back to the previous example, you have your signal here. You decrease the resolution by a factor 2. You have this signal, and this is what you have lost during this degradation. And when you do it again, this is what you have lost, and so on. So all the information of your signal is in all these coefficients and the last part, which is a very smooth part. Okay, because from this one plus this one, you can recover this one. From this one plus this one, you can recover this one, and so on. So all the information is on the right part plus the last one here. And then you have everything. And now the good point is, the question is, when you want to have this one, you don't have to come back from your data. You can just start from this signal. Because everything which is here contains the information which is here is contained in this one. So you don't have to come back to the data to compute this one. You can directly compute this coefficient from this signal here. You can compute this coefficient from this signal which is here. So you can define this way fast operator, and that's answer to the question. You go from one resolution to another one using filters. And here I introduce two filters, H and G. And you are doing the wavelet decomposition with these two filters. You are not using anymore the wavelets or the scaling function. So these two filters will allow you to have a fast algorithm in n log n. And so you go from one resolution, CGA to CGA plus 1 by convolving your data by a given filter. And you will get the wavelet coefficients by convolving the information at a given resolution by another filter, which is filter G. And typically, H is a low-pass filter, and J is a high-pass filter. And because all the information of CJ is contained in WJ plus 1 and CJ plus 1, you can reconstruct CJ from the coefficient that you have computed. So it may be a bit complicated. So to understand exactly what we do, it's a cascade algorithm. We start from the data, we convolve by H, and we take 1 pixel out of 2. We convolve by J, and we take 1 pixel out of 2. And this is the wavelet at the first scale. Then you do it again. You convolve by H, you take 1 pixel out of 2, and by J, 1 pixel out of 2. Then you get the wavelet at the second scale, and so on. So by this way, you have a fast algorithm. So you start from the data, convolve by H, 1 pixel out of 2, you get this guy. You convolve by J, you get this one. Now you are on a new resolution, V1. You convolve by H, you get the guys at the second resolution. You convolve by J, you get the wavelet coefficient at the second resolution, and so on. What you see at the end, here you had n pixels, but you have divided by 2 here and here. So the sum of the number of pixels by here and here is still equal to n. And then here, again, you divide by 2 the number of pixels and by 2 the number of pixels. So you can easily see that the total number of pixels, when you take all the wavelet coefficient plus the coarse resolution, is still n. You still have the same number of coefficients. Okay, so compared to the previous algorithm, the continuous wavelets, we had a number of pixels which was multiplied by the number of scales. Here, we always have the same number of pixels. It's an orthogonal decomposition. We have no redundancy. So this, just to give you an idea how it works, this is a signal with 4 pixels. Do you understand how we compute the wavelet transform with the Haar wavelets? I'll let you remember that the Haar wavelets, the filter H is just 1 over 2, and the filter J is 1 over 2 minus 1 over 2. So these are, yeah. Can you read? Okay, so these are the Haar filters, H and J. And using these 2 filters, we want to compute the wavelet transform of this signal. The solution is there, but do you understand how we can compute this solution? The solution is the last line. No? No idea? Exactly. So the best guy is always at the first line, you know. Okay, so you see that this one, 56, is just the sum divided by 2 of the 2 first terms. So you apply the filter H, 1 over 2, 1 over 2, okay, and you divide by 2, you get this one. Then you take the 2 next one, divide by 2, you get this one. So here, this is the convolution by H. Okay, now by J, you divide by 2 and you take the difference, and then you get this one. Then you take the 2 next, and you get the second one, and so on. And now you make the cascade with the first line, and you get these 2 and these 2, and then you make the third cascade with these 2, and you get this one. So this is the Haar wavelet transform of this signal. Just to give you an idea. Yeah? Clear? So Haar filters, and they are related to the wavelet and the scaling functions. So you know that one wavelet coefficient here is a scalar product of your data with the wavelet function, which is the Haar wavelet. But the way that you compute it is using the filters, because it's faster. Okay, so just to give you an idea, so here we have the signal convolved by H and G taking 1 pixel out of 2. What happens in the Fourier space? In Fourier space, when you do that, you divide the Fourier domain in 2 parts, the high frequency and the low frequencies, and this part is related to W1, and the low frequencies is related to the coarse resolution. And this one, you redo it, you make the cascade here, so you decompose it in 2 parts, low frequency, high frequencies, and then you get W2, which is here. And you can repeat it until you go to the larger scale. But everything, that's what you are doing in Fourier space, but all operations are done in the direct space using the filter H and J. Exactly as we did it here with Haar filters. You don't go to the Fourier domain. Okay, that's very fast. The wavelet function, which is the wavelet function which will be related to G, will always have a 0 mean. Otherwise, it's not a wavelet. So you have to see the wavelet function as something which captures the difference between 2 resolutions. Okay, so you remove the kind of continuous part. So when you go to any question? So if you go to 2 dimension, in fact you have 3 wavelets in 3 directions. orthogonal, vertical, and diagonals. And then you decompose your image onto 3 wavelet functions, which are in 3 directions. And I will show you why we have this. You start with one image, and on this image, you take one line, and you apply this H and J filters. So doing this, you take one line, you apply H, and you take 1 pixel out of 2, you obtain one line here. And you do the same with J, and you obtain one line here. And you repeat it for each line. So you obtain 2 sub-images, which have n pixels in height and n over 2 for the width. Okay? And now you repeat the same process, but column per column. So you take one column, you convolve by H, you obtain, taking 1 pixel out of 2, you obtain this image, and convolve by G, you obtain this one. And you do the same for the other one. So you decompose your image into 4 sub-images. And the 3 images which are here correspond to wavelet coefficients. And this one, which is convolved by a low-pass filter in both directions, correspond to the coarse resolution. And it is on this one that you repeat the cascade. So here what you have is one image. You take the wavelet transform, you obtain 3 directions plus the smooth part. You reiterate on the smooth part several times, and then you get this image. So what is important to see here is, first, you see that most of the pixels here, they are black. It's not 0. It's just fluctuation around 0. So most of the information is contained in the highest coefficients. That's the first one. For the detection, it's also much easier because in all these pixels, you have a 0 mean because of the wavelets. By definition, by construction, you have a 0 mean. So it means that if you add a constant to an image, or if you have a background on your data, the background will have no effect on all these coefficients. To detect something, you just have to compare the fluctuation around 0 due to noise. Is it compatible with noise or not? If it's not compatible, then you have signal. But you don't have to care about the background anymore, because the background will be completely at the coarser scale. That's an important property. Another point you have to keep in mind, these coefficients here have a 0 mean. That means that they have some positive and some negative coefficients. It's not positive image. Even if your image is positive at the beginning, the wavelet coefficients have a 0 mean, contains negative values. So this is the basis of the JPEG 2000 image compression norm. That's a new norm. And just to give you an idea, the difference between the standard JPEG image, so this is an image, and then here's compressed using JPEG techniques. So there's a compression ratio of 768. It means that the number of bits you have on your computer is divided by 68 compared to the original image. And here is the same, but using wavelets instead of a localized cosine. And it's a bit better, so you don't have this blocking effect. It's not perfect. It's not perfect because you have some artifacts around the edges. You see them. And this has motivated other decomposition. But clearly it has been shown on a large class of images, so it's using really a huge database, that in practice, for compression, wavelets are doing a bit better than JPEG. And typically you have you can win something like 20% in terms of compression ratio. So it took 10 years for the wavelet community to end up with something which is better than JPEG, and the improvement was 20%. So now my question is, have you ever seen a GP2 image on your computer at some point on the web or somewhere? You do? You did? Okay, 1. Anybody else? Whoa, 2. Normally this is 0. So very few people are using the new norm, even if it's better. And the question is why? It's just why companies, they just don't care about 20% improvement. 20% improvement in terms of disk. They have better disk. They double the capacity of the disk every 18 months. So to change the technology for only 20% of improvements, they are just not interesting at all. Because the disks are on your iPhone or whatever, they are just improving so quickly. So just improving by 20% is just negligible. So it was a bit frustrating for people working wavelets because they work very hard, they find filters and very good wavelets with good properties and everything. And at the end, they got the new norm, they showed that was better, but nobody cared. So compression, obviously, is not the point where wavelets led to a significant result in terms of practice. You will see it's different from other things. So this was the orthogonal. I don't present the bare orthogonal, but they're very similar. So it's already a second kind of wavelets decomposition that you have seen. You have the continuous wavelets, which is one kind of dictionary, and then you have these orthogonal wavelets, which correspond to another kind of dictionary. And very, very early, in the early 90s, we have seen that this orthogonality is a problem for image restoration. Already in my PhD thesis, I had your age at this time. I was switching from orthogonal to redundant wavelets because I saw that using orthogonal wavelets, you lose a very interesting property, which is invariance per translation. It means that if you take one image or one signal and you shift your signal by 1 pixel and you take an orthogonal wavelet, you get different wavelet coefficients. It's because of this decimation step. So can you avoid this decimation step, but still keeping fast algorithm? And the answer is yes, you can do it. You can do it using what you call undecimated wavelets. So now, what you are going to do is you are keeping the same framework as before, but now you are going to remove this step of throwing away 1 pixel out of 2. So what you have at the end is still a decomposition with filters, but what you introduce is what you call holes in the filters. So at the next resolution, instead of throwing away 1 pixel out of 2, you introduce holes in the filters. And the beginning, so the number, what is interesting is the number of operations will still be the same because we don't compute the multiplication by 0. So we have still convolution by the filter H and the filter G, but we don't remove 1 pixel out of 2. So it's more standard convolution. And how it works, so we go from one resolution to the next one. At the beginning, it's just a standard convolution by your filter H, but at the next step, you take 1 pixel out of 2 when you compute this point. But then you will compute all the other points. You don't throw away 1 pixel out of 2. So you have, this way, a very fast algorithm using a property of the filters. So I don't show the math, but you can, there is some clear math why you can do that, because of the property of the scaling function, which is called dilation property. So I won't enter into the details. Just know that you can have very fancy way to compute a fast transform using undecimated wavelets. And in 2 dimensions, the same, you have the 3 direction. So how it works this way. You start from an image, you convolve by H, but this time, one line will have the same size as the line in the original image. And you convolve by G, and you get exactly, the line will be the same size as your own image. So when you repeat now in the column direction, you obtain 4 sub-images, but each of them has the same size as the original image. Okay? So we don't reduce the size of the images. So your transform now is what you call overcomplete. It's redundant. But then you keep the invariance property. And this is the wavelet transform of this image, Einstein image, so that the wavelet coefficient at the first scale and the second scale in the 3 directions, and that's the coarse resolution. And you can reconstruct this image from all these wavelet coefficients. And you can decide to remove the, to to introduce the decimation, in fact, at the level where you want, and you can have some kind of partially undecimated Fourier transform. But this is just a game. In practice, people are using only orthogonal or undecimated wavelets. So now to give you an idea how important it is when you do image restoration to not decimate. So what I'm going to do is I'm adding some noise on this little Einstein image, and I take the Fourier transform, I apply the thresholding technique that I showed you before, just remove some coefficients, and reconstruct. The threshold will be the same using the orthogonal decomposition and the undecimated decomposition. So the only thing we change in the two results is the decimation. The only step we change. So this is the image. This is the result using orthogonal wavelets. I take the orthogonal wave transform, I threshold all coefficients which are smaller in absolute value than 3 sigma, and I reconstruct, and I get this image. And here is using undecimated wavelets. In terms of image quality, so you see that just going to orthogonal wavelet to undecimated wavelets, there is something like 3 dB difference. So it's a huge difference in terms of quality of when you are using undecimated wavelets. You can understand this also under the way that you have a dictionary which is larger when you use undecimated wavelets. When you are using orthogonal wavelets, at the final scale, for instance, you are using a wavelet only at 1 pixel out of 2. You are not putting your wavelet function everywhere. When you are using undecimated wavelets, you are putting the wavelet function everywhere. So if you go to larger scale, it's even more important, because when you are at the larger scale, you are putting in the orthogonal decomposition your wavelets only 1 pixel out of 16, 64, and so on. Okay? Because of all this decimation step in cascade. When you are using undecimated wavelets, you are just putting your wavelets everywhere at each pixel. So that's the reason why it works so much better. So now we have seen that the extension of the orthogonal wavelets to the second dimension has been done introducing 3 wavelets in 3 directions. And this was been done to have this kind of algorithm which was separated in line and columns. In astronomy, very often, we don't have directional features. If you are looking at stars or more or less isotropic galaxies, you don't see really any reason why we should have vertical or directional duration. Doesn't really make sense for this kind of images. So the idea was, can we have isotropic wavelets without any directions? So we want just to analyze at different scales, but without having these 3 directions, which doesn't make too much sense in many applications in astrophysics. And this is what you call the starlet transform. Starlet because it's very well good for astronomical images. People in biomedical imaging are also now very often using this kind of images and this kind of decomposition. So the idea now is to have filter H and G, which are isotropic. And I'm going to show you how we can compute these kind of filters. And so this can be done very easily if you now see that, if you consider that the wavelet coefficient is just the difference between 2 resolutions. So you have one image, you degrade the resolution by factor 2, and what is lost, the difference, is your wavelet coefficients. So you define your wavelet function as the difference between 2 scaling functions. And then you immediately see that the reconstruction algorithm is very straightforward. Because if you define your wavelet coefficient as the difference between 2 resolutions, then you can immediately see that the reconstruction is just a summation of all wavelet scales plus the coarse resolution by construction. So taking an isotropic wavelets like the basepline, so this is a basepline scaling function and this is a basepline wavelets, it really looks like a Mexican hat, but it's not a Mexican hat. And this is very important because the Mexican hat doesn't have the property to derive fast algorithm. You cannot have a filter H and G related to the Mexican hat because you need a compact support for the wavelet. And using spline, you can have a wavelet function which is very similar to the Mexican hat, but which have the right properties in terms of scaling function, and then you can derive H and J filters, and you can have a fast algorithm. So the filter H is just this one, so you can apply it. It can be separable in line and column, so you have these filters in 2D, but in practice you apply it in 1D, in line and in column. And, okay, boundary is not too important here. And when you apply the filter H, you go from one scale to the other one by smoothing it this way, just repeating the filter H in cascade. And the information that you lose when you go from this scale to this resolution, the difference is your wavelet coefficient. And so these are your wavelet coefficient, and you have the coarse resolution, and the simple addition of all the wavelet scales will produce the original image. So here is the standard transform of your original image into 5 wavelet scales plus the coarse resolution. So now when you do a denoising, that's something which is important here. When you will apply a denoising, you will not apply the thresholding on the coarse part. You apply the thresholding only on the wavelet coefficients, because these are 0 mean. Blue here is 0. Okay, so these are fluctuation around 0. So when you detect or you threshold, you compare just the fluctuation around 0 in all these wavelet scales. You remove some coefficient, and you can just add everything. And that's the reconstruction is very simple. And you can also very easily follow what happened in the different scales. And so another point you should notice as well is when you have a feature somewhere, you have always a ring around, and this is related to the wavelets. That's the specific properties of wavelets. If when you have a direct image, you convolve by the wavelets, you find the ring of the wavelets, you find it in your wavelet coefficients. So you see, that's the reason why you have a 0 mean. Okay? So now, just to give you an idea of what you can do, very simple thing you can do with this starlet transform. Dynamic range compression. Sometimes you have in an image feature with different contrast. For example, you have a star which is order of magnitude larger than another one. So if you look at the image, all you see is this star, or you see the other one, but you cannot see the two at the same time just because your eye cannot see them. So we can try to make contrast enhancements, taking the logarithm of the wavelet coefficients. So now we are going to make an artificial image. It's not a real image. An artificial image, just taking the logarithm of each wavelet coefficient and then make the summation of all the wavelet scales. And this is the equation. So I take the logarithm of each band and I sum everything. I just put the sign of the coefficients on top of it. And here, for instance, a comet image. So that's the right time to speak about comet. And so this is the image. If you make a histogram equalization, you know what is histogram equalization in Photoshop or any software for image processing? You can change the lookup table in a given way so you see better the feature in the data. Okay, so histogram equalization, you will provide this image. So you already can see that the comet is much larger than what you are seeing on the image. But if you are using now the logarithm of the wavelet coefficients, here what you get. So now you can really see features at different scale appearing. So you have jets, matter of jets in the comet. So that's a very easy way to find features in the data at different scale. So that was just a small example. So that was the parts on wavelets. So any question about wavelets here? Okay, so I'm not expert of this kind of feature, but the guy I gave the software at this time. At this time, what he was doing, he was trying to have a model. He was looking for this feature. So what he was doing, he was using a model on his data of the distribution of matter, and he was subtracting his model to the comet to try to identify this feature. And it was very hard because if his model was shifted by 1 pixel, he can change the solution. And he was very impressed that just doing this kind of very simple rotation, you can so easily identify them. But you have to keep in mind that this is an artificial image. The value which are here doesn't make any sense. It just allows you to see what is in the data. Okay. Go ahead. It's a bit slower because there are more pixels, but the number of operations to go to one scale to the other one is still the same because the filters, because they only add 0 in the filters, so the number of operations per pixel is the same, but you have more pixels. So it's a bit slower, but in practice, it's very fast. Yeah. It's still n log n. Yes? No. There is 2 points. You can have sparsity doesn't mean orthogonal. You can have a huge dictionary with many, many features in it, okay, and still have a sparse notation in this dictionary. What you don't have is the fast transform doesn't provide you the fastest, the sparsest solution in this dictionary. Because okay, you can represent the same data because it's not orthogonal, so you can represent the same data in different way in this dictionary. But here, so for restoration, there is another thing which is important. And for this, I would like to see if you know what. Imagine that now, okay, so that's a good point to address the problem. Imagine that you have an image with noise. And in this image, I know that I have this small laser pointer in the image. Okay, it is somewhere, and I want to find it. What is the best function to detect my laser pointer? What should be the best tools to detect it? Sorry? Exactly. Because that's a match filter theorem. Okay, if you are looking for a shape, the best way to detect the shape is to use the shape itself. You correlate your data with this shape. So if you know the shape, then just use it. Then when it starts to be complicated, it's if you don't know exactly the size of the pointer, the width of the pointer, the orientation of the pointer, then you say, oh, I have to multiply by all the shapes, the position, the size, and the rotation. Then it starts to be complicated. But the point is, ideally, in your dictionary, you should contain the shape of the feature that you are looking for. Because then you optimize the cross-correlation, the sign-to-noise ratio when you cross-correlate your functions with your data. So if you use undecimated wavelets, you will have a better restoration because imagine that you have a feature somewhere. Let's remove this. So imagine I have some noise, and somewhere you have a feature which is here. So if you apply, and the noise can be quite large, you don't know the size of the bump that you have in the data. Okay, it can be small, large, so that's the reason why you may want to use something like wavelets. The optimal function to detect these kind of features is clearly to convolve by a Gaussian which has this shape. So you are really at the location, and you have to put it at this place. So, but then you don't know. Then the reason we're using wavelets is then you have a fast transform, and you have all the scales and everything. So you are going to use wavelets. If you are using orthogonal wavelets, you will put your function so only at one point out of, I don't know, maybe here and here. So you will have your Gaussian, which may be here, and another one which may be here. So you don't put your function at the location where you have your bump. So you decrease your signal-to-noise ratio. And the reason why to use undecimated wavelets is you have a dictionary which is larger and which puts your analysis function everywhere on the data. So undecimated wavelets is a larger dictionary, but still having fast computation. And I told you that there was always this trade-off between the quality of the dictionary and the computation. You may want to have many, many shapes, all the shape of the universe, but then you don't know how to compute the coefficients. Okay, so the idea of this fast wavelet transform is you n log n, you get your coefficient. And now you have seen that we have already several wavelet transform. We have the continuous one. We have where you can put any function for the wavelets. We have the orthogonal wavelets, and we have the undecimated wavelets, and we have the starlet transform. So we see that you have already 4 dictionaries, and each of them will be well adapted to some kind of feature in the data. So you can play with this dictionary. Okay, that's a really one point is there is not a universal way to analyze the data, and this will be really one message of my talk. There is not a single dictionary which is universal. You can select one dictionary rather than another one for a given problem, and you can design your dictionary, and you may even improve your results. So this was for the wavelet part. Okay, so what's going on here? So what time before lunch? Okay. Okay. I will start and we'll see tomorrow. Okay, so we have seen we have already several dictionaries. And starting at the end of the years 90, people were thinking that maybe wavelet is not optimal for everything, especially if you are looking for lines in an image. Some very specific features, then wavelets are certainly not optimal. And then there is the whole story of X-let transform. So everybody starts to find his own X-let decomposition. Ridgelets, curvelets, bandlets, surfacelets. So everybody in the community wanted to have the best transform, and there was every month a new decomposition. So I'm not going to present all of them to you. I think even not all of them here. I'm just going to show you ridget and curvelets. So I've already shown undecimated and isotropic wavelets. So to understand why people were thinking that wavelets are not optimal for edges in images, is that imagine that you have one edge and you want to represent this edge with wavelet coefficients. Then what you will see is that you will need a lot of wavelet coefficient to represent this edge. And the idea is to have other kind of functions which are more directional, which have more different scaling properties. And then using this new function, then you can have a better approximation of this edge with less coefficients. And that's the whole idea. To understand better this, imagine you have this image. Can you see what is in this image? It's not the laser pointer, it's something else. The signal-to-noise ratio is 0.1. Okay, we are far from 2 sigma, 0.1. So by eyes, just impossible to see anything in the image. The question is, if you have some prior, sometimes you can do something. And having a given decomposition is a prior. When you say, I'm using the Fourier transform because I'm looking for periodic stars, it's a strong prior because you think that you have a periodic feature in your data. Okay? When you use wavelets, you have another prior. Your prior is your data are more or less isotropic with feature of different scales. It's not a strict prior because you can represent many kind of data using wavelets. But your optimality will be when your prior will exactly represent the data, when your dictionary contains the shape contained in the data. That's the prior which came when you do sparsity. You assume that your dictionary represents properly your data. So here, if you have a right prior, you can try to see if in a given space you can still see something, even if in the pixel space you don't see anything. And okay, so if you don't say too much how to do that, I'll give you some information. I know I suppose that my feature is in one direction only and is infinite. Infinite means the size of the image. So knowing this prior, what you will do, you will integrate all the information along the column. And then you end up with this signal. And now you can see that you have a feature which is here. And if you integrate over the width of the feature, then you will have a kind of 5 sigma detection. So if you know exactly this information that your feature in the data are in a given direction, then you can integrate along the direction and you can detect something. If you were using wavelets, you won't detect anything because the dictionary is not adapted to the data. If you were using widgets, you would have detected 5 sigma as a feature. And the interesting point here is when you are using widgets, you don't say at all what is the direction of the feature. You are analyzing using widgets all the direction. So whatever the rotation of the bar I have in the data, with widgets, I will have seen the bar with the 5 sigma detection. So you can detect something which is very faint if you have a prior which is correct and help you to take into account the correlation of the information in the data. But you need to have the right dictionary for that. So here, widgets was just perfect for this kind of data. So the continuous widget transform is just a kind of extension of the wavelets. It's a directional wavelets, but directional is infinite. So you have a function now, psi, where in addition to have the scale parameter and the location parameter b, you have also the orientation parameter. So this is the widget function. It's infinite in one direction, and if you cut in the other direction, if you make a cut, then you have this wavelet function which appears. So the widget function has a zero mean, exactly as the wavelet function. So you can decompose using widgets, thresholds and coefficient in the same way you were doing it with wavelets, and you can reconstruct. So the question now, how can I compute in all direction with all the widths the transform of an image? And this can be done if you see that the widget transform can be written as a two-step operator, while the first step is the Radon transform. Who knows who is the Radon transform? What is the Radon transform? One. So the Radon transform is something very well known in medical imaging, because every time you have a scanner of your brain or whatever your body, so it turns around, you have the instrument which turns around you. What the instrument is measuring is a projection of what happened in your body. So what you have, the measurements are projections, and you have to reconstruct from this projection the signal. That's every time you go for medical exams, is exactly what happens. They do an inverse Radon transform. And the Radon transform can be seen as a line. So one point of the Radon transform corresponds to the integration along one line in the image. And there is a very famous theorem, which is projection-slash theorem, which shows that you can compute the Radon transform from the Fourier transform. So the point is then you can just take your image, compute the Fourier transform in 2 dimensions, extract line going through 0 in the Fourier domain, and take the inverse Fourier transform of this line. And then you get one line of the Radon transform. And then you can show that the widget transform is nothing else than the one-dimensional wavelet transform of the Radon transform. So on each line of the Radon transform, you apply your wavelet transform. and then you get widget coefficient. So it's a kind of sequential step of operators, 2D Fourier, 1D inverse Fourier, 1D wavelets. And then you get widget coefficient. Each of these steps is reversible, so you can reconstruct your image from the widget coefficient. And to understand why it works this way. So I told you that 1 point of the radon transform corresponds to the integration along one direction in the original image. So if you quad the information along 2 adjacent points, it's similar to integrant over bars. So you integrate the information over bars. And then you have all the direction, and you have this way, a way to decompose your image with all direction and all widths of the bar. But the length is infinite. Okay? That's a widget transform. You can localize this analysis. So this is the local widget transform. I told you that the length was infinite. And if you know that you are looking for features which are not of the size of your image, you can say, OK, I'm looking for feature of 10 or 15 pixels or whatever. So you can make block, and each block of the image, you apply a widget transform. It's a localized widget transform. This is just to give you an idea how it works. That's an image. I have just added here Poisson noise. So that's the data. So from this data, completely blindly, you go to the widget space. You have the right threshold related to the Poisson noise, and you reconstruct, and you end up with this image. So you can really recover features which are very faint. So here, most of the pixels are 0 in this image. And you can still recover very well the 2 bars. So having the right prior here clearly helps you to get something reasonable, while any other dictionary here or anything else will have led to some very bad results. So one of the fundamental problems of the widgets is to give the size of the lines, right? I told you that it's infinite, or you have to localize and to fix a given size. So the idea of curvelets is to have different sizes integrated in the transform, so you don't have to care anymore about the size, the length of the feature in the data. So the idea of curvelet is to have a decomposition where the supports of the function follow these scaling properties, which is proportional to the length of the square. And here are the kind of curvelet functions that you are going to use for your analysis. So you have different orientation, different width, and then you can decompose your image in this dictionary, which is completely directional. And to compute the curvelet transform, you can do it using the Starck transform first. You use the Starck transform I showed you before. So you have several scales. And at each scale of the Starck transform, you apply a partitioning. You decompose into blocks. And on each block, you apply a widget transform. But then from one scale to the other one, you change the size of the blocks. And by these techniques, then you have what you call a curvelet transform. Okay, so to schematize the algorithm, we start with an image. You apply the Starck transform. At each scale of the Starck transform, you make a block partitioning. And now, on each block, you apply the widget transform. And the widget transform is, again, Fourier 2D, Fourier 1D inverse, wavelet 1D. So it's a mixture of many things, but at the end, you get new coefficients, which follow some properties for the dictionary. So you have also a fast curvelet transform, because it's a bit painful to have all these steps. And the fast curvelet transform has been proposed by Candes again and Laurent de Manet. And the idea of the fast curvelet transform is to try to extract directly from the Fourier space the information relative to the curvelet coefficients in a given direction. And you can see that I have to give one specific curvelet bands belongs to a given wedge in the Fourier space. So to get the curvelet coefficient, in fact, you have to extract all these wedges. So the idea was to try to make a 2D inverse Fourier transform directly of the wedge. And the problem is that the wedge is not rectangular. So you cannot directly apply a 2D inverse Fourier transform. And the idea was to use the periodicity of the Fourier transform to transform a parallelepiped into a rectangle using the periodicity. So you start from a wedge and you make it a rectangle. And then from this rectangle, you take just a 2D inverse Fourier transform. And then you get curved coefficients. So it's a very easy way to get a curved decomposition. You go into the Fourier space, you extract this wedge, and you take 2D inverse Fourier transform, and you get curved coefficients. So just to give you an idea of what is the impact of different dictionary for denoising. This is an image where you have clearly directional features, part of Saturn ring images. So this is a noisy simulated image. If you use the starlight transform, the starlight transform is good for directional features. So directional features is clearly not the case here. So here we see what kind of result we have. If you use the undecimated Weyl transform, so it's a bit better because now you have 3 directions and it's more adapted to this kind of image. This is what you have. And you see some kind of small artifacts. And the artifacts have always the shape of the elements in the dictionary. Because you have an artifact when you have a fault detection. You detect something when you have nothing. And then what you reconstruct has the shape of the dictionary. And here we're using curvelets. And you see that with curvelets, you have a better reconstruction of all the edges in the image. So curvelets are clearly much better for this kind of feature. Now I have a claim here that using tools like the curved transform, I can play with edges. And I will show you that this is true. And to see that, you're again now going to play with contrast enhancement. I will show you that you can really play with the edges in an image. So here we have, I introduced a function here, which is to modify the curved coefficient. And this function is artificial again. What I'm going to do is, for small coefficients which are close to the noise level, I don't touch them. I keep these coefficients unchanged, and I increase artificially the coefficient which is a bit larger than the noise. And then for very large coefficients that you can very easily see, again, we don't touch them. So we are going to change only faint coefficients, but larger than the noise. And then reconstruct the image from the modified coefficients. This is the original image, and this is just increasing some coefficients artificially, just to show you that you can, for instance, if you look at the ring, you can clearly see much better all the features which are in the data. Just playing with the edges. The data are there, but by eye, just because of the contrast, you don't see the faintest feature. And you can, and this was also a study on the comets, which had been done by the US. It was in 2005. And they had a problem again with the optic. So the goal of this project was to study, at this time they didn't put something directly on the comet, but the idea was to send a rocket on the comet, and then at the impact, there's some material which are thrown away, and then with the camera you can investigate what is inside the comet. And the problem is, again, a problem with the optic. And just by doing with the edge, you can see that you recover much better all the crater on the comet. This is a picture of the port of Marseille. And if you look at the waves, the ports, again, just playing with the edges, you see much better all the waves which are in the water. So that's another way to play with the curved coefficients. Deconvolution, this is the real data of Saturn. Using sparsity and curved constraints, you can recover from infrared data, you can recover this image starting from this one. Just to give you a kind of idea or how we can use sparsity to make inverse problems. So tomorrow I will address more in details how these tools, sparse tools, can be used for different inverse problems. So I will present you different applications in radio astronomy, in painting techniques, and also maybe CMB as well. Thank you. And if you have any questions,